Hello everyone, this is Hamidi Mandal and today I am going to explain about the Digital Signal Processing Laboratory Experiment 4, that is the study of discrete Fourier transform DFT and application on recorded PPG signal. So let's look at it. So what is the discrete Fourier transform DFT? The discrete Fourier transform is the transform that deals with a finite discrete time signal and a finite or discrete number of frequencies. Specifically, given a vector of n input amplitudes, the discrete Fourier transform yields a set of n frequency magnitudes. That is x of k equal to sum over n equal to 0 to n minus 1, x of n e to the power minus j 2 pi k n divided by capital N, where capital N is the number of samples in time domain. So what is the need for DFT? Now, as we know that real world signals are analog signals, that is continuous in time and hence infinite values, and computer cannot handle infinite values. So they need to be sampled in time domain. So to get the frequency spectrum of the sampled signal, we perform DTFT, discrete time Fourier transform. But the spectrum of DTFT is continuous, and since the same problem arises, so it needs to be sampled. So sampling in frequency domain leads to the discrete Fourier transform or DFT. Now today's lab experiment is finding pulse period with DFT from the recorded PPG signal. So what are the steps? Now the first step is we need to apply the moving average filter to smoothen out the high frequency noises present in the PPG signal. Then DFT of the signal is found out, and after that the maximum or peak location in the DFT, the index is found out. So the first peak is taken in magnitude response. The corresponding frequency for index k is obtained is by the formula frequency equals to k into sampling frequency divided by length of signal, and the pulse rate is obtained at 60 into above calculated frequency. So let's look at the assignment and codes. The question is find magnitude spectrum of a signal sampled at 100 Hz using DFT algorithm. Use metric representation of DFT to compute DFT coefficients for a given signal with duration of 3 seconds. And compute a period of a signal and compare with autocorrelation based period estimation method. So first the array is there, x of 75, the 3 second, and the signal is sampled at 25 Hz, so 75 samples are there. So one array of y75 and the DFT matrix of 75 cross 75, but both are separated, real part and imaginary part. RDFT represents the real DFT matrix and IMDFT the imaginary DFT matrix. And then RX, IMX and MAC DFT are declared. Now we write the code in void setup so that the calculation is just done for once, and in void loop we will print that saved calculation. So first at void setup serial dot begin equal to 9600. Now we applied moving average on the signal x of I and we got y of I, that is the smoothened signal. Now on that smoothened signal we are calculating the real DFT matrix and imaginary DFT matrix. That is for k equal to 0, k less than n minus 1, k plus plus. For r equal to 0, n less than n minus 1, n plus plus. RDFT k n equal to the real part is cos 2 pi k n divided by n, and the imaginary part is minus sin 2 pi k n divided by n. So in the next part we are multiplying the matrix with our signal values. So for int k equal to 0, k less, in the inner loop we are multiplying with the signal values and storing that at rx of k. And now we know mag DFT of k equal to square root of square of our real part plus square of imaginary part. So now we need to find the maximum, right? So we declared the maximum value and maximum location. Now we put one loop that is iterating, and we go up to 70, the first 75 values, and we stored the location, and now frequency equals to maximum location into what we told is that uh, into the number of samples divided by the uh, frequency at which the signal is sampled. So maximum location into 75 divided into 25 divided by 75, that is maximum location divided by 3, I have written directly. And pulse rate equals to 60 into that frequency. So in void loop, once we are printing the like magnitude plot, that is printing mag DFT of I. And if we comment this one and put the second part, then it is like the printing in the pulse rate. So let's look. This is the magnitude response what we plotted through the DFT algorithm. And next we calculated the pulse rate calculated through DFT is 80. And in the previous experiment, I have discussed the autocorrelation method to calculate pulse rate or pitch frequency, that things. So the pulse rate is calculated through autocorrelation or the previous code is 71.43. So error percentage is approximately 11.997. Now we have to do the same experiment in MATLAB. So let's look at the MATLAB code. So the first 3 lines is here, this is in clearing the previous inputs. Now we load the data. Then we are basically declaring the fs and that things. Now we are applying the moving average function in this part. The logic is same. We calculate in MATLAB DFT is like FFT function is there. So if we directly apply FFT, it will give the matrix. So we applied the inbuilt functions and we calculated the DFT and DFT matrix values. Now we need to find the maximum of the DFT. So we stored the index of maximum and we plotted the magnitude response. And the pulse rate is calculated 60 into index into fs divided by size of filter. Like this is the size of the data, that is 75. Now we need to calculate through autocorrelation. So for autocorrelation, we can directly subtract the mean and then we can find the correlation, and we plotted the autocorrelation also, but we didn't show it here. We will show the magnitude plot only. Now we need to find the zero crossing. So by declaring some zero crossing index equals to 0, we checked where the slope is like the correlation of I plus 1 into that of I less than 0. That location is the zero crossing, so we break it there. Now in the next part, we are just calculating the pulse rate and printing that. That's it. So here one in index correlation, when we are finding the index of the maximum, there we need to figure out that we are finding the maximum index from the first zero crossing. So we need to add the location of the first zero crossing also to get the actual index. So we got like that, we got the pulse rate. So this is the magnitude response plotted in MATLAB. And then the pulse, as you can see the terminal, the pulse rate calculated through DFT is 80 same, and the pulse rate calculated is 71.4286 through autocorrelation. So the error also same, 11.999%. So the thing is, the code logic is same, just to once we applied in Arduino and another time in MATLAB, so the values won't differ, but the writing approach different. So what we learned is basically that DFT can be applied to get the pulse rate from the PPG signal. Thank you.